Hello and welcome to lecture 23 of the course Computational Complexity. In this lecture, we will see Oracle Turing machines, right? So we have seen reductions and Oracle Turing, which are many-to-one reductions, many-one reductions. Oracle Turing machines are another way to view reductions using what is called an oracle. Okay. So if you Google for the word Oracle, right? Obviously there is this software company called Oracle Corporation, but if you for the English meaning of the word Oracle, so this oracles were people who were in like some in ancient times or mythologies or whatever, people who used to be maybe in maybe in the courts of kings or maybe otherwise, who used to provide kind of advice supposedly from the gods or from the future or somewhat prophecy type of things, right? I've pasted a snippet of the Wikipedia entry for the word oracle. So they are people, so oracles were people who were consulted in order to get like advice, right? So this is keeping this in mind. Let's try to understand the word what are Oracle Turing machines, right? So Oracle Turing machines are Turing machines which have access to an oracle. What are oracles? So oracles could be so we will first define oracle as a specific problem or specific language. So it could be for instance, I think in this lecture mostly we will use the SAT oracle. Okay. So we know that SAT is an NP complete language. So a SAT oracle, if you write down a SAT instance, if you write down a Boolean formula, the oracle will immediately tell you whether this formula is satisfiable or not. So this is what the oracle does, right? So you get the yes or no answer immediately and the correct answer. So it's not just any yes or no answer, right? So an Oracle Turing machine has the functionality or has a way to ask the oracle queries and get responses, and can use these responses in its computation, right? So it can make the SAT query many times if it has a SAT oracle. It need not be a SAT oracle, it could be any oracle, right? So it could be a three-colorable oracle, right? So whenever you give it a graph, it immediately tells you whether the graph is three-colorable or not. So the oracle is it's an oracle, right? So it doesn't take any time. You give it, it immediately gives you the answer back. Yeah, so you give the question, it immediately gives the answer back. It doesn't take any time. It is just one step. So how is it like how is it formalized in this notion? So it's a Turing machine, right? And it has a special tape called the oracle tape or the query tape, right? And on the query tape, the Turing machine will write queries, right? So queries, or it need not write in one step. It could be constructed in a sequence of many steps. But and so if it's a SAT oracle, it will write a SAT instance. So when the SAT instance or the query is ready, at some point it will go to a special state. The special state being the Q query, right? The first one is Q query, denoted by Q with a question mark in subscript. Some textbooks may say Q query. And then the next step, the oracle gives the response. How does the oracle give the response? It will look at the query tape or the oracle tape. So it doesn't need time to read or anything. It's just one step. And then it will immediately move the Turing machine to the yes state or the no state. So these yes state and the no state are also special states. So all of these three are special states: Q query, Q yes, and Q no. So if it is a yes instance, it will move to Q yes. If it's a no instance, it will move to Q no, right? So this is what it does, right? And an Oracle Turing machine is a Turing machine with these properties, right? And the oracle could be any language. Like as I said, it could be SAT, it could be three-colorable, it could be subset sum, it could be like two-colorable, anything, right? So depending on how powerful the language that corresponds to the oracle is, you'll find different we'll find different results, right? So how does it function? I've already described, but I will just go through it again. The oracle is the oracle corresponds to some language. So here we are denoting that language as A, right? So it has access to the A oracle, right? The language A oracle. So in what I described, the oracles possible are like, it could be like I said, SAT or three colorable. Any language can be used as an oracle, right? And at some point the string is written on the query tape or the oracle tape. Maybe I'll just try to. So there are Turing machine tapes. Let's say this is the work tapes. Let's say these two are the work tapes, and let's say the black one is the oracle tape, right? So this is the oracle tape. The other ones are work tapes or the query tape. So it will keep filling up the oracle tape, and then it will move to a state, the oracle state Q query or the query state, and then depending on what is there on the oracle tape, it will move to Q yes or Q no. So if it's a yes instance, it will move to Q yes. Right? This is what basically the oracle will check whether the string is a part of A or not a part of A. This is what happens. And such an oracle is called, or such a Turing machine is called, if a Turing machine M is there with access to an oracle A, it is denoted by M with superscript A. So it has M and it has access to the oracle A. And we will see later, we will see generalizations of this, where we will see complexity classes with access to an oracle. Okay, so we'll define what they are. We'll soon see, and we can even define, again, this we will not quite do, but we can do that. If you see textbooks, you may see this notation where complexity classes have complexity classes as oracles, right? So where both the subscript as well as the superscript are both complexity classes, right? So let me just define the first one. C1 with access to A means, so it's a complexity class. So first we'll use P superscript A to define it. So basically you have a deterministic polynomial time Turing machine, right? So what is P? P is a collection of languages decidable by deterministic polynomial time Turing machines, right? But now P superscript A means it is the class of languages decided by deterministic polynomial type Turing machines. This is exactly what it was for P, but with access to an A oracle, right? But with the access to an A oracle. So this red underlined part was not there for P. So that is the access to the oracle. NP superscript A is again the same thing. So what is NP? NP is a class of languages decidable by non-deterministic polynomial time Turing machines. NP superscript A is the class of languages that are decidable by non-deterministic polynomial time Turing machines with access to an oracle A, right? So again, the red underlined part at the end of the sentence is what changes, right? So this is what a complexity class superscript A means. It is the same machines that form part of that complexity class, but with access to an oracle A. C1 superscript C2 will not define now, just to avoid making too many definitions, right? Okay, this is the notation. So what is the reason for making this definition, or what is the motivation behind this? So we have seen many one reductions, right, which is denoted A less than or equal to subscript M B, right? So although we didn't define it in this course, you must have seen it in the theory of computation course that in your undergrad. But the same principle applies for the polynomial time and log space reductions, both of which we saw in this course, right? So what was the principle there? So the principle was that W is in A if and only if f of W is in B. So basically we are transforming an instance of A into an instance of B. So you are transforming A instance W to a B instance f of W, and then using that to solve A. So basically converting A instance to B instance and then using an algorithm of B to solve A. Correct? This is what we did in the many-one reductions or polynomial time or log space reduction. So many-one reductions is just the same thing, except that there is no restriction on the time or space used by the machine. But polynomial time and log space are specific cases of many-one reductions. So Turing reductions, right, which is what we are going to define now, or there is one issue, or there is one specific limitation with the many-one reductions or log space or polynomial time reduction. So basically you convert the problem instance and then use the decider for B to decide A. So this can be viewed as asking the decider of B just once, right? So you just convert it and then ask the decider for B, is it in B or not, is the converted instance in B or not. So basically we are getting only one query to ask the B decider. So why not ask the B decider many times? Do we get any advantage out of that? Do we get any benefit by allowing us the greater possibilities of asking B many times? So that is what Turing reduction does. So Turing reduction is basically an access to an oracle of B. So when you have an access to an oracle, you could ask queries to the oracle multiple times, not only once, right? So the question here with many-one reductions was, why can't we query B multiple times, right? And that is what is addressed by the Turing reduction. So basically we say A Turing reduces to B if A is decided by a Turing machine M with access to an oracle B, a B oracle, right? So we'll see one simple example. So one is which is very simple, and maybe you might feel it is silly, but even this simple or silly example illustrates the power of Turing reduction over many-one reductions, right? So the simple example is that SAT complement is reducible to SAT using Turing reduction. So subscript or less than or equal to subscript T indicates Turing reduction. SAT complement is reducible to SAT. So what does it mean? It means that there is a machine with access to a SAT oracle that can decide SAT complement. So given a SAT complement instance, right? So let's say given a formula phi, it is in SAT complement if it is not satisfiable, or in other words, if it is not satisfiable, it is in SAT complement, which means it's a yes instance of SAT complement, right? So which means it's a no instance of SAT. So basically all that we do is we ask phi to the SAT oracle. If the SAT oracle says that it is a yes instance, you answer no, and if the SAT oracle says it's a no instance, you answer yes. So which is what is written here. If the SAT oracle accepts, you reject, and if it rejects, you accept. So basically you flip the output of the SAT oracle. So you start with an input, you just write down the input in the query tape, ask the SAT oracle one query and flip the output, right? So what we have shown here is, if this is a machine M that does this, we have shown that SAT complement is decided by, okay, maybe that's small, is the language of this machine M with access to SAT oracle. And if you notice, all that M is doing is just writing down the input in the query tape, which can be done in linear time, and then flipping the output, right? So this is certainly linear time. So M is a polynomial time machine, a deterministic polynomial time machine. So I can as well say that. So we can as well say that SAT complement is in SAT complement is in P superscript SAT. It is in P with access to a SAT oracle, right? Because M is a polynomial time, deterministic polynomial time machine. In fact, it's not very difficult to see that even SAT, maybe I'll write it above. It's not very difficult to see that even SAT is in deterministic polynomial time with access to SAT oracle, right? Because it's trivial, because you want to solve SAT and you have access to the SAT oracle, then all the machine has to do is just copy into the query tape and make the query, and then accept or reject accordingly. The same thing without flipping. And in fact, now SAT is a NP complete language. SAT complement is a co-NP complete language, and we have seen that using Turing reduction, you can reduce a co-NP complete language to an NP complete language, which was not possible if we just used polynomial time reductions as we had learnt. Right? So you see that Turing reduction is actually more powerful. Even though this particular example was extremely simple, you see that even the simple example illustrates this fact. Right? So SAT is an NP complete language and SAT complement is a co-NP complete language. So in fact, both of them are contained in P superscript SAT, which means that the entire class NP is contained in P superscript SAT, P with access to SAT oracle, because SAT is contained in P superscript SAT. Right? Because you could take any NP instance, you can reduce it to a SAT instance and then ask and SAT is in P superscript SAT. And co-NP, likewise, you can reduce it to a SAT complement instance, and even that has been shown to be in P superscript SAT. So both NP and co-NP are in P with access to a SAT oracle. And notice that P with access to a SAT complement oracle is the same thing, because if you get yes no answer, a SAT complement will tell you whether it is not satisfiable or satisfiable. It is the same thing that SAT oracle also tells you, just that it answers the flipped output. Right? So you take the answer of the SAT oracle and flip it, you get the SAT complement oracle. Right? So P superscript SAT, which is equal to P superscript SAT complement. So NP and co-NP are both contained in that. Right? Maybe two exercises. The first exercise is to kind of see how, or for you to see how powerful is this idea of making multiple queries to a certain oracle can be. Right? Suppose you have a SAT oracle, right, which tells you yes or no given a SAT instance, whether it is satisfiable or not. Now please construct an algorithm which, given a Boolean formula, if it is not satisfiable, then you just output it's not satisfiable. If it is satisfiable, then actually the algorithm should provide and should output an assignment, a satisfying assignment for the formula. So if given phi, it should tell, if phi is satisfiable, it should tell a satisfying assignment for the formula phi. Right? So try to construct this using a SAT oracle, and you will need, and what I am telling you right now is that you will need to make multiple calls to the SAT oracle, multiple queries to the SAT oracle, but still you can find it. And the idea used in this is very, it's not that difficult to find, but if you think hard, you can find it. And the idea used in this will be useful for a theorem that we will see later in the course, right? So this the idea used here, maybe I'll just tell the name of the idea. It's called self-reducibility. Okay. But anyway, you don't need to know what self-reducibility is, etc., to answer this exercise. Just try to see. So maybe what the first step is, let's say you given a formula phi, you just give phi to the SAT oracle. So SAT oracle will say whether it's satisfiable or not. If it is not satisfiable, you are done, right? Because there is nothing to be done. If it is not satisfiable, there is no satisfying assignment. If it is not satisfiable, you are done. If it is satisfiable, then you have the task of producing a satisfying assignment. Think how you will go about this, right? So remember, the SAT oracle can take any formula, any instance of satisfiability as an input. So what instances can we give? Think about this. Next exercise is to show that if A is in P, okay, if A is in P, then the class P with access to an A oracle is P itself. Okay, so we saw that P with NP is contained in P with access to a SAT oracle. NP and co-NP are both contained. But however, that was for SAT. If A is in P, right, then P with access to an A oracle is actually P itself. So obviously P is contained in this direction is easy, right? P is contained in P with access to an A oracle, right? So usually, just again, this is one of these things I will just say. Whenever you have to show that two sets are equal, two classes here in this case are equal, one of the standard ways to go about doing this is to show that the left hand side is a subset of the right hand side and the right hand side is a subset of the left hand side. So in this case, P is obviously contained in P with access to an A oracle, right? Because P is, well, P itself. So even without accessing the A oracle, we can say P is this. So A oracle only adds more power, right? But the other direction, P with access to A oracle, we have to show that it is contained in P. This will be, again, this is not very difficult to see because A itself is in P. A is also a polynomial time. A is also decidable in polynomial time. So instead of asking the oracle, this machine itself can run the algorithm for A. So that is why the other direction, P with access to A oracle, is contained in P. That's how that comes about. That is a slightly that will require a bit of explanation, but the other one is even easier, right? And yeah, that's what I want to say in this mini lecture. Just defined oracle Turing machine, which is a special type of Turing machine which allows us to ask an oracle some queries, right? And I defined M superscript A as a machine M with access to an oracle A, and P with superscript A is the complexity class, machines in complexity class P with access to an oracle A. Likewise, NP superscript A, we define Turing reductions as instead of reducing it to that language, you can have oracle access to that language, right? So Turing reduction is A Turing reduced to B if there is an oracle Turing machine M such that A is the language of M with access to oracle B. And finally, some simple inferences using for these complexity classes and the exercises. And that's all I have for lecture 23. Thank you.